Pleasure to welcome everybody to the Friday CUNY online set theory seminar. And today it is my great pleasure to present Benedikt Löwe, and he is going to speak to us about analysis and higher analogues of the reals.
Well, thank you. Thank you very much. I don't really need to see myself, right? Okay. Thank you very much for the introduction. I'm going to talk about higher analogues of the reals, and this is, in some sense, for those of you who have heard about this research area, connected to the area that is sometimes called generalized Baire spaces. So in particular, so generalized Baire spaces is this area where people look, instead of looking at omega, they look at kappa to the kappa and study properties of kappa to the kappa. With the exception that today we are quite deliberately not looking at kappa to the kappa. So instead of, so of course, as set theorists, we are used to saying omega to the omega is the reals, and we are usually not looking at the real reals, the Datakins completion of the rationals. What we are going to do today is we are going to look precisely at fields like this and replace the usual study of the set theorist of kappa to the kappa by the study of the appropriate field that take the role of the reals in these higher analogues. So we are trying to find the R analog, or the kappa analog of R, I should rather say, right? The kappa analog of R. And look at kappa real analysis. And of course, for kappa real analysis, we really need the analog of R, because as we know, this doesn't usually work on Baire space very well. Okay, so let's start. So we start with Datakins theory. So Datakins tells us that at the level of the reals, there is a unique, complete, ordered field. And of course, one of the questions that we can ask is, what do we actually mean by complete here? So there are two different interpretations of complete. One would be Datakins complete. So that means my broadcasting has just stopped. How did this happen? Datakins complete, so that means every bounded set has a least upper bound. Or we could think of Koshi complete. So that would mean every Koshi sequence converges. And of course, I suppose you know the answer. What we want here is Datakins complete. As we will see in a moment, Koshi complete is not enough for this for this theorem. And in order to illustrate what type of fields we are talking about, I want to go through some of the basic steps of this argument briefly. So the fields we are looking at are ordered fields. So we have the field structure and an order. And the order respects plus and times in the sense that if you add something positive, then you get bigger. If you multiply with something positive, the multiplication is order preserving if it's with something positive. And one of the main steps of the proof of Datakins theorems is to prove that Datakin completeness implies that the field is Archimedean. So a complete, an ordered field always contains the natural numbers because, well, it contains a copy of isomorphic to the natural numbers, right? It has 1, 1 plus 1, 1 plus 1 plus 1, 1 plus 1 plus 1 plus 1. And because it's a field, this means it contains the rational numbers. And Archimedean just means that the natural numbers are cofinal in K. So why is that? Well, suppose they are not. So if n is not cofinal, then it is bounded. Then by Datakins completeness, it has a least upper bound. Completeness. There is a least upper bound. Let's say this is, what should we call it? Let's call it S. So that means the whole set N is completely below S, -1. That exists in that field. It must be less than S because the order is compatible with the algebraic operations. So because this was the least upper bound, this one cannot be an upper bound. That means we find some K such that S minus 1 is less than or equal to K, but then S is less than or equal to K plus 1, and therefore S was not an upper bound. Okay, so as I said, this is one of the key features of the proof of Datakins theorem, and what we observe is that we have this sequence that lives in that field. So if a field is non-Archimedean, then we have this sequence that is bounded but doesn't converge, right? It can't really have a least upper bound. Let me briefly discuss the consequences for the field that we get from this. So, of course, if n is cofinal, then the set 1 over n converges to 0. And similarly, if we have very large fields, so if K is a field that has no countable cofinal sequence, then of course we can have no countable sequence converging to 0. Then no countable sequence converges to 0. This is, of course, one of these features of fields that by inverses you convert cofinal in the field to converging to 0 and vice versa, and by translations in the field you can move everything everywhere. So that means converging to 0, the behavior of things converging to 0 is the same as behavior of things converging anywhere else, because you can just shift them to that place. And that gives rise to the following definition. I think that at least the name is due to Dale and Wooden. So the base number of the field. And the base number of the field is the smallest length of a sequence converging to 0. Sum S from kappa into, my kappas and my k's look very similar. So this is okay, let's call it lambda then. Converging to 0. So as we have seen, if the field is Archimedean, then the base number is Aleph 0. If the field is non-Archimedean, then in principle it could be larger. So the goal that we have is find a field with uncountable base number in which we can do real analysis. Okay. Let me briefly say something about, well, I should say a few things about convergence, and I promised to say something about Koshi completeness. So let me say a few things about this. So first of all, convergence. The convergence that we are talking about here is, of course, convergence in the order topology of the field. And I'm only stressing this because we are, there is a tendency to think of this as a metric topology. But of course, one has to take the word metric with some caution, because the official definition of metric is of course that you have a distance function that goes into the reals. If you take that definition and you define convergence with this notion, then of course convergence is tied to convergence of length, of countable length, because you have the rationals. What we are thinking of here is rather take the field itself as reference point for the metric. So that means that the distance of x and y is just the absolute value of x minus y, and therefore this distance function is a function that goes from k into the positive or 0 numbers in the field. And then convergence really means the same thing. The epsilon criterion of convergence is really the correct criterion. So that really means that a sequence S from lambda to k converges to 0 if and only if for all epsilon in k plus there is an alpha such that for all beta bigger than alpha, S of beta is less than epsilon. Right? That's the usual definition, except that, of course, here we are not looking just at reals, but at arbitrary positive elements of the field. And the same applies for the notion of Koshi sequence So that means when we say a sequence is Koshi, what we mean is for every epsilon, there is an alpha such that for all beta and gamma bigger than alpha, the distance between S of beta and S of gamma is less than epsilon. And then you have a notion of Koshi completeness that says every Koshi sequence in this sense converges to something in this sense here. Now, what about, I promised, let me go back one page. So I promised to say something about why Koshi completeness is not enough. So Koshi completeness is not enough for Datakins' theorem. And that is because we can always build, for every field, we can build its Koshi completion. And we observe that the original field lies dense in its Koshi completion, and therefore the base number is the same. So that means if you start with a field that has base number bigger than Aleph 0, then its Koshi completion will have a base number bigger than Aleph 0, and therefore by this argument, it will not be isomorphic to the reals. So Koshi completeness is not enough, and that is in some sense the driving force of everything that we are going to talk about. So we are looking at, if you look at Datakins' theorem, you could at first think maybe there is no such analog for higher base numbers because Datakins' theorem just tells you that anything that remotely looks like the real numbers is the real numbers. The way we get around this is that we give up Datakins completeness and we work with Koshi completeness. Okay. Any questions so far? Then let me now move to finding the first example of this. If you have ever taught basic...
Wait, could you just repeat again the definition of base number? I mean, we just went by, I mean, so it's the shortest sequence that converges to 0. Okay, so lambda is an ordinal here, or
lambda is a cardinal.
Cardinal, yeah, okay.
I mean, you could define it to be an ordinal, and it will be a cardinal.
Right. Well, it'd be regular cardinal, probably. Right?
Yes.
Yeah. Okay. Right. And then what was that? I mean, that quick and dirty rendition that you gave in turn just now about yeah. All right. I don't know. You said the argument again in summary, and then I mean I was trying to grasp it in terms of this definition.
The argument of what?
I'm trying. Well, I can't quite remember what you're trying to prove. What you were just discussing. The failure of one of these notions
was that Koshi completeness is not enough for Benedikts theorem.
Yes,
and that is because you can so take under the assumption that there are fields with higher base number, but that's so we will see constructions in a moment. So if you take anything that has base number Aleph 1, let's say, you build its Koshi completion, which is just the standard construction, except of course that you have to be you have to use the notion of
the values in the field itself. Yeah.
Yes. Otherwise, it doesn't make any sense.
Yeah.
Then you get a Koshi complete field that extends the one that you started from, but the one that you started from lies dense in it, and therefore the base number is the same. Because
oh, that's the point.
And so if the base number is still Aleph 1, then it can't be isomorphic.
Okay.
Right?
Okay. Is the base number just the same as the cofinality of the fields?
Yeah, in fields, of course, it happens to be the same thing, right? By precisely this argument here. Why doesn't it want? Here we are. And that's the magic of inverses. Okay, so here comes the simplest construction you can come up with, and it's a construction that I think almost everyone who has ever taught a basic introduction how to reconstruct things set theoretically out of the natural numbers immediately thinks, okay, let's do it let's, instead of starting with the natural numbers, we start with an infinite and uncountable cardinal. And we just build the same object that the reals would be, except that it's now longer. So the idea is do the standard construction of the reals, but start with, say, well, actually I should start with kappa, because it's kappa R that we are constructing. So in kappa in general will be an uncountable cardinal. So I just did this in class, so it's very fresh on my mind, but maybe for some of you it's not that fresh on your mind. So how do you do this? You start with the natural numbers. You observe that they are a cancellative monoid, and then you realize that cancellative monoids can be, you just take the integers become the equivalence classes of pairs of things that have the same sum. Or in this case, you could also just think of this as an ordered structure, and you just add all of the minus values. And then what you end up is a ring, and then you take Q as the quotient field. Actually, not just a ring, but without zero divisors, of course. Otherwise, it won't work. Right, and then after you have the rationals, you usually in the set theoretic introduction, you would now take the Datakins completion, but we already saw that this might be not what we want. So then we take the Koshi completion, which of course in the case of the reals is exactly the same. Okay, so let's do the same thing for kappa. Well, we do precisely the same. So we do kappa and add all of these, let's call it minus kappa, right? So these are the additive inverses of the elements of kappa. And then we take the quotient field. So that means the things now look like plus minus alpha divided by beta, where beta is not zero. And
okay,
then,
so wait, I'm frightened all of a sudden, right? So I mean, I know what these, I mean, the operations on n, which I guess is omega, if you're right, I know those.
Adam, you have heard this talk.
I know, and I'm still afraid.
And this is why you are saying the thing that I'm going to say next.
What?
So Adam has actually had precisely this talk in February, and this is why he's always one step ahead. And
I'm also pre-clearing you for Warwick. No, but anyway, I'm just wondering if I missed something, because you start off with the cancellative monoid, and I don't see where the structure's coming from.
No. I was going to spring this on you in a moment, that there is a problem.
Okay, sorry. Okay, I spoiled your.
So you take the quotient field, and then after that, of course, you just take the Koshi completion, which. Oops. And let's call these things, so this is kappa, of course, itself. Then this thing is kappa Z, and this is kappa Q, and this then is kappa R. Perfect. And as Adam already pointed out, this is not quite as easy, because obviously the addition and multiplication on kappa are not commutative, and not all of the distributive laws hold. So if you do this with a non-commutative thing, then what you get here is not a proper object. And therefore, there is no reason that this would actually give you a proper clue. So instead of ordinal addition and multiplication, you need to use what is sometimes called the natural. Use the natural addition, or some people call it the Hessenberg addition. So this is the one where you add the terms of the Cantor normal form in the appropriate way and make sure that the thing becomes commutative. And then things work. Okay, so that is indeed a field that has base number kappa if kappa is regular.
Sorry, Benedikt.
Yes.
Can you say a little bit more about this Hessenberg thing? I don't think I've ever seen that before.
Oh, so what you do is you take alpha and beta, write them in Cantor normal form, and then you just group the exponents in the appropriate way. So if you have I don't know, omega squared plus omega plus 1, and you have omega squared plus 7, and then you group them together and you get omega squared times 2 plus omega plus 9, or whatever I said. And that gives, these are the natural operations on ordinals.
Could I just ask, so in principle, you could use any arithmetic structure on a kappa-sized object and do this construction, no? So you could just use the upward Löwenheim's golem or something like that.
Yes.
So you know you can endow a kappa-sized thing with an arithmetic structure that satisfies what you want.
Yeah, it's mostly, so for example, I'm going to do some calculations in a moment, and then of course it would be nice to actually have some intuition what these numbers actually mean. Right? I would like to know, for example, that 1 over omega is smaller than every 1 over n. Right?
Sure. Yeah. No, I just wanted to check. So this basically means that you can run this construction, this completion construction, basically on any thing that has addition and multiplication that satisfy the laws of that you have in the natural numbers, or in V, if you will. Right.
But you need the ordering, right?
Right.
Well, if you want that the base number is kappa, you want to start with something that, as an ordered structure, has height kappa. Right? Because as Andreas was pointing out, the cofinality of the field is of course the same thing as the base number because of the inverses. So you want to start with something that has the right length. But other than that, it doesn't matter what the arithmetic on the structure looks like. Right? There's no, actually, the question is potentially more complicated than I thought. So according to my knowledge, and maybe someone can refute that, it's not completely impossible to have a field structure where the cofinality of the field is not kappa, but the size is kappa. That should be possible. So you shouldn't start with one of those if you want to get base number kappa.
So you can take just an increase, take some nice big field and take a field that contains it not inside, but adding new stuff at the end. And then take another, do it again, do it for omega time. You got something big, but the cofinality is omega. Yeah.
Okay. So this is Sikorsky's, we call it Sikorsky's kappa R because this was already done by Sikorsky in the 1940s. And here is a reference to his paper, first of all, and the theorem that he proved about this. So if kappa is uncountable, then already kappa q, so not kappa r, but the kappa rationals satisfy the Bolzano-Weierstrass theorem. Again, we need to be slightly cautious about what it means to satisfy Bolzano-Weierstrass. So Bolzano-Weierstrass usually, let's just write it down informally for a moment. It just says every bounded sequence has a convergent subsequence. And of course, usually when we are working over the reals, we don't really have to say what we mean by sequence, because there's only one type of sequence indexed with natural numbers. In our world where we have longer sequence, we know that short sequences cannot converge. Right? And if the base number is Aleph 1, there cannot be countable sequences that converge. So that means you can easily construct a bounded sequence that cannot have any convergent subsequences just because it's too short. So take any sequence, cut it off at omega, then that sequence is an omega sequence which will still be bounded if the original one was bounded, but it will not have any convergent subsequences because it is too short. So that means in the world—
I guess you want it to be not constant, right? The sequence in your example.
Yeah, yes, yeah, you're right. Constant sequences still converge even in yeah, I think you're absolutely right. If I go back, then even here I should have stated not constant zero. Otherwise, so that means in this world of kappa fields, we have to— what is happening? This is the second time this happens. So in this world of kappa fields, we want that this is a kappa sequence, because otherwise we don't really have any reason to assume that it would be convergent. So why does this imply that it is Cauchy complete? Well, because Cauchy sequences are bounded, and Cauchy sequences can have at most one limit point. So if it has a convergent subsequence, then the whole sequence converges. So that's what Sikorsky proved of his field kappa q, but what does that mean? So if kappa q is already Cauchy complete, then kappa q is equal to kappa r, because that was the Cauchy completion of kappa q. And what is the cardinality of kappa q by construction? The cardinality of this is just kappa. And that is an indication that this field does not behave like the reals, right? Because one of the things that we have of the reals is that we have a topology base that is considerably smaller than the cardinality of the whole thing. We have a dense set that is much smaller than the whole thing. And all of these things cannot be true here, because kappa r has just cardinality kappa. So its cardinality is equal to its base number. So this suggests, and we will see in a moment that it actually really does mean that, that kappa r does not really behave like the reals. Okay, and I'm going to now show you an example why that actually is the case. I do this on the next page or here. Let me. So what I'm going to show is that kappa q equals kappa r does not satisfy the intermediate value theorem. So it has lots of gaps. Okay, how do we do that? So we define a function f from kappa q, kappa q into 0, 1. I guess, what is your favorite formulation of the intermediate value theorem? Is it with 0? Or it doesn't really matter. So we define the following function and we say f of x is equal to -1. Well, let me define the +1 case and the other one as otherwise. 1 if there is a natural number n such that 1 over n is below x and -1 otherwise. Now that doesn't look like a continuous function. It clearly does not satisfy the intermediate value theorem, right? Because there is a point where it's -1, and then there is a point where it is 1, and it does not have a 0 in between. So clearly doesn't satisfy the intermediate value theorem. But of course, that's not a problem, because there are lots of things that don't satisfy the intermediate value theorem. We need to show that this is actually continuous on our field. So need to show f is continuous. How do we do that? Well, we show that for each of these for each of these sets, these are convex sets in the field. If I take a point where it is -1, there is a little epsilon ball around that where it is still -1 everywhere. And if I have a point where it is 1, then I have an epsilon ball where it is 1 everywhere. So if that's the field, so here's 0. Here is this sequence 1, a half. This now looks very ungeometric. We know that this sequence cannot converge. So there is this weird. Let's draw it as a green blob, right? This is where the lack of the greatest lower bound is there, and we now have that this function has the value -1 down here and +1 up here. And we want to show that if I take any value over here, then I can still find an epsilon ball. And if I take a value here, I also can still find an epsilon ball. Now in the upper region, this is clear, right? In the upper region, I just take an actual rational and find a rational spaced ball around this. So clearly, if f of x equals 1, I find epsilon even rational, such that for all y in x minus epsilon, x plus epsilon, f of y is equal to 1. And that's even true in the rationals. Now, if f of x is -1, then what do we do? Well, then we add 1 over omega. So then consider x plus 1 over omega. Well, if that thing has gets value 1, if f of x plus 1 over omega gets value 1, what does that mean? Well, that means that there is some 1 over n that is below it. Then find.
I'm sorry. What's omega here now?
Omega is the ordinal omega.
Okay, but wasn't there a whole long discussion about how the ordinals themselves are irrelevant and there's just some general constructs? So how do I get my hand in terms of the order structure?
Well, that's precisely what I said when Gunther brought this up. I said one of the reasons why I don't want to do this on an arbitrary thing of
I see.
is precisely for this calculation.
Okay, I'm catching
right?
up. Okay,
This is why I don't. I really
fine point
want
the structure's relevance.
Yeah.
So good.
So we find an n such that 1 over n is less than x plus 1 over omega. But now, of course, that means that what is it? That then if I add if I take 1 over n plus 1, oops, it's the end of my page here. So then 1 over n plus 1 must be less than x, because the difference between 1 over n and 1 over n plus 1 is bigger than 1 over omega. So that means that f of x is already equal to 1. And this shows that we really have this little epsilon. Well, actually, we know what the epsilon is, right? It's a 1 over omega ball around this thing. Okay, good. So it doesn't satisfy the intermediate value theorem, and as we see, the proof that it doesn't satisfy the intermediate value theorem is very closely related to the fact that we have these sequences that are not converging. So here's a different approach for another field. So the property that Sikorsky Q equals kappa R is lacking is saturation. That is actually the model theoretic property of saturation, or it's equivalent to the model theoretic property of saturation. But we express it now in this way. So a field is saturated if for all sets that are where all of the sets of the left side are below all of the elements of the right side, and both of these sets have cardinality less than the base number, then I find something that sits in between. And so that is saturation for these fields, and Sikorsky's kappa Q is not saturated. And one of my co-authors, Lorenzo Galeotti, constructed a, why is this happening all the time? You will, sorry. Galeotti constructed a field that actually is saturated and satisfies the intermediate value theorem. To be very precise, you can't get it for continuous functions on these fields, but for kappa continuous functions. So you have to weaken the notion of continuity a little bit. And I can very briefly tell you what this field is. For those of you who have seen the surreal numbers, it is actually a pretty natural thing. So surreal numbers are presented in this way as sequences, surreals as sequences from some ordinal into plus minus. and Conway had this this idea that in some sense, if you add a plus, then what you get is the least complex the least complex number that sits between this one and the, well, you can always describe these as gaps, and you find the least complex number in the gap, and that is then presented by adding a plus or a minus. Now, it doesn't really matter for what we are doing, but if you now look at the serials of sequences that have length less than kappa, serials with descriptions on alpha less than kappa, then this allows you to define R kappa as the Koshi completion of Q kappa. And what you get is a field that is saturated, Koshi complete, real closed. It has cardinality 2 to the kappa, as it should, and it has a dense subset of size kappa and base number kappa. And indeed, it is the unique one. So this is sort of the Datakins theorem for these fields. Okay, so what did we have for Sikorsky? For Sikorsky, we had that the field satisfied Bolzano-Weierstrass, right? So what do we
could I,
have?
sorry, yeah. Could I just ask, what's the size of this R kappa? Is it kappa to the kappa, or?
Yeah, 2 to the, yeah.
Okay, sure.
So size of R kappa. That follows directly from the fact that it has a dense subset of size kappa and is saturated.
Sure.
And that's, of course, what from the point of view of a generalized Baire space research, of course, we want that our analog of the reals is in bijection with kappa to the kappa. Everything else would make the theory completely useless. So, so we want we want a topological connection between kappa to the kappa with a usual Baire space topology, generalized Baire space topology, and this, and we get this in this way. So what about Bolzano-Weierstrass? So now we have the intermediate value theorem. If we also get Bolzano-Weierstrass, then we are very, very happy. You see whether I still have some, yeah, I do have some space here. So let me state the theorem, maybe on the next page, which tells us that if K is saturated and has base number bigger than Aleph 0 and a dense subset of size kappa, then it can't satisfy Bolzano-Weierstrass. Well, so that's bad news. So in particular, this means R kappa does not satisfy Bolzano-Weierstrass. So that means we have that there is this in the abstract. I mentioned this. There is tension between Bolzano-Weierstrass being valid, which works on fields that are not saturated, and the intermediate value theorem, which works on saturated fields, and these can't be true together. So let's briefly argue why this is the case. So we need to construct a sequence that has no convergent subsequence. So what we do is the following: we take any omega sequence in K. Here it is. We know, because it's an omega sequence, it must be bounded, right? So so since it's an omega sequence, it can't be cofinal. So there is something that sits here. Let's call this X. Okay, and now what you do is you use the saturation and the fact that you have a dense subset of size kappa in order to create, by recursion, a kappa sequence, a descending kappa sequence that goes all the way to, let's call it the top of this omega sequence. And so you find, you apply separation to this and that. Right? These are both sets of size less than kappa and find something here. Then you apply separation to this and that, and you find something here. Then you apply saturation to this and these three, and you find something there. And you continue, and using the density of the set of size kappa, you also make sure that you really hit everything there. So using saturation plus density, of set of size kappa, find again, okay. At some point I will understand why it keeps doing this. Find decreasing kappa sequence that is cofinal in the set of upper bounds of the omega sequence. Right, so the set of upper bounds of the omega sequence is a convex subset of the field, and I take a dense subset of size kappa, and using the dense subset, I make sure that I get something that is cofinal in the upper bounds. Now, that is a kappa sequence. So if Bolzano-Weierstrass is true, if Bolzano-Weierstrass holds, then this has a convergent subsequence. But it's a strictly decreasing sequence, right? So that means it must be convergent. So it's convergent. But of course, whatever it converges to must be the least upper bound of the omega sequence, because there's no space between the omega sequence and this thing that we constructed. But its limit is the least upper bound of the omega sequence. But that can't be, because we know it doesn't have one. So saturation and uncountable base number implies that you can't have Bolzano-Weierstrass. Okay, so maybe this is the end, right? Maybe this is just what we now observe. That if you go up in the base number, in the intermediate value theorem and Bolzano-Weierstrass, and you have to pick, and that means your analysis will be strange in one of the other ways. And that is not the final answer, because, and this is what I'm now going to end with, well, I'm going to talk about our main theorem, and there should be also some set theory involved. So far there was very little set theory, as you noticed. If you weaken Bolzano-Weierstrass, then you actually manage to get versions of Bolzano-Weierstrass that can hold in saturated fields. And the way that we weaken Bolzano-Weierstrass is by demanding stronger boundedness properties in the statement. So you remember Bolzano-Weierstrass says every bounded sequence contains a convergent subsequence. And so if you strengthen the requirements of boundedness, then you weaken Bolzano-Weierstrass. And here's the diagram with our properties. So this property, totally bounded, is from a paper by Kiesler and Schmerl, who used this in the context of non-standard analysis. Here is the property that we had in our paper, being interval witnessed. And as you can see, being a Koshi sequence implies being totally bounded and being bounded. So in particular, if you say every bounded sequence contains a convergent subsequence, or every totally bounded sequence contains a convergent subsequence, it still implies that every Koshi sequence converges. So the Kiesler-Schmerl version still implies Koshi completeness. However, the weak Bolzano-Weierstrass version, so that means every interval witnessed sequence contains a convergent subsequence, does not necessarily imply Koshi completeness. And in fact, it doesn't, because one of the main lemmas that we proved about this is that if K is a subfield of L and K is cofinal in L, and L satisfies weak Bolzano-Weierstrass, then K satisfies weak Bolzano-Weierstrass. So, I mean, this is, of course, very, very different from the setting of Bolzano-Weierstrass, right? So, for example, you have the reals, you have the rationals. The rationals lie dense in the reals, but the rationals do not satisfy Bolzano-Weierstrass because they have lots of Koshi sequences that do not converge. And this, in particular, this means that if you take, for example, our kappa, that is a Koshi complete field. If that satisfies weak Bolzano-Weierstrass, then also every cofinal subfield, including Q kappa, which is not Koshi complete, satisfies weak Bolzano-Weierstrass. So you immediately get non-Koshi complete fields that satisfy weak Bolzano-Weierstrass. Okay, so this is these two properties, so the Kiesler-Schmerl property and the weak Bolzano-Weierstrass property are now our candidates for being versions that can survive living in a saturated field. And so indeed, that is precisely what we then investigated. So here's the theorem. And this is by the 4 people that were mentioned, right? Merlin Carl, Galeotti, Hanafi, and myself. So the theorem is if K is an ordered field, base number of K is bigger than R of 0, K is saturated. Actually, we only need a weaker version called spherically complete, but it doesn't matter here for this talk. There are some interesting questions about spherical completion as well. Then the following are equivalent. One, K satisfies. And 2, kappa has the tree property. I could say a few words about the proof, although this is one of those theorems where the proof is actually not the most interesting thing, because the proof is really, so if you have ever seen the connection between Bolzano-Weierstrass and Weak-Koenigs lemma, so think of Bolzano-Weierstrass versus Weak-Koenigs lemma. So you have a sequence, a bounded sequence. So that means there's this interval, and my sequence elements live somewhere here in this interval. Now I'm trying to find a convergent subsequence. So what do? I build a tree by splitting this into halves. And I know that at least one of the 2 halves will contain infinitely many of the values of the sequence. Without loss of generality, we are dealing with sequences that have no repetitions. Right? If we have infinitely many points that are the same, then of course we find our convergent subsequence. And I iterate this. So I build a binary tree and I know that there will be a path through this tree by Weak-Koenigs lemma, and that path determines, because I'm working in a metric space in the reals, so that means I'm reducing the size of these intervals in each step. So I know that this sequence converges, and that means that the elements that I find in these little intervals, the ones that are still infinite, will produce a convergent subsequence. Right? That's the classical proof of the Bolzano-Weierstrass theorem using Koenigs lemma. And that's essentially what we have implemented for this theorem, because the tree property gives you the same thing, except, of course, that in this setting, everything is slightly more complicated because we have limit levels of the trees. And at the limit levels, there might be bad things that are happening. Well, there have to be bad things that are happening, because if everything goes without any problems, then of course we could prove full Bolzano-Weierstrass, not just weak Bolzano-Weierstrass. So at some point we will have to use that we have these stronger boundedness conditions. So what happens in the proof is the following: when you get to a limit point, you somehow want at the limit point also an interval that represents what is happening at this limit point. Except that, of course, suppose you do this for omega many steps and you reach the first limit point, then of course the boundary values are omega sequences, which means they don't converge, which means you can't take their limits as the limits of your interval. So that you need some help in order to extract from these sequences of convex sets that are shrinking some interval that you can then use in order to continue. And I mean, the language already suggests why our interval witnessed sequences are really good, because they are, I mean, as you can see, I didn't even write this in proper mathematics. I only gave this informal description. So for every epsilon, I have a family of intervals that covers almost all of the elements. And that is precisely what I need in this proof in order to continue beyond the limit stages. So this is why the proof is not terribly interesting. It is the same proof, and the only problematic step in the proof is the one where we are precisely using our property. On the other hand, if you look at the statement of the theorem, you suddenly realize that it can't be a completely random result, because it does identify, notice that it doesn't matter what the field is. Right? So the tree property of kappa is independent of which field with these properties you choose. So if kappa has the tree property, if it's a weakly compact cardinal, then all such fields will have weak-walled sum of Weierstrass, and vice versa. If it doesn't have the tree property, then none of them have this. So that tells us that this is not just something where we constructed a completely artificial notion that fits the proof, but there is a phenomenon behind this that we identify. And the phenomenon really has to do with identifying the right level of strength that you need in order to extract this type of convergence. So in particular, since our kappa has these properties, so what we get as a corollary is that if compact, then R kappa is a field on which we can do some sort of real analysis. And with this, I would like to close.
Okay, thank you. Let's see. Are there any further questions for Benedikt?
I've got one.
Yep.
It actually, I mean, so now that you went through the explanation of the why you were taking the more well, the explicit approach using ordinals, as opposed to some hand wavy Lowenheim-Skolem thing, which might have, and you know, and then I was wondering about something, because a few years ago I was reading some of the literature on, I mean, there's surreal numbers on the one hand, and there's you know, some classical model theory of ordered fields, and in particular saturated models, and the relation between them. And I mean, it's a tight relation. I mean, in some sense, I mean, except for being a proper class, Conway's field, you know, is, you know, sort of, yeah, it's the monster saturated example, so to speak. Now, on the other hand, the specific feature of Conway's construction makes use of and highlights other structure, which might not be preserved by all order automorphisms, right? And I'm wondering if, like, the particular role of your omega there is an instance of that. I mean, is this resonating with you at all, or no? I mean, it's been a long day here. It's like all of a sudden I spotted that, and I was actually reading about things like this a few years ago.
Well, so that the field that we are looking for will turn up as a subfield of the surreals is of course not surprising, because
Right.
the surreals are the monster real.
Right, but not by any sort of unique embedding, presumably.
That it shows up really as a quite natural thing. So if you do the same for omega, so if you look at the
Oh, so it does come by natural then. Okay.
So if you look at Q omega, Q omega in the surreals is actually not the rational numbers. Right? If you take all sequences of finite length, what you get is the dyadic rationals. However, the dyadic rationals are dense in the reals, and so if you take its Cauchy completion, you actually end up getting the reals. If you go one step further in the Conway construction to sequences of length exactly omega, well, of length less than or equal to omega, so you add all of the omega length sequences, then you overshoot. Right? Then you actually do get all of the reals, they are all included now, but you also get numbers like omega, minus omega, which obviously are not real numbers. So I'm not sure whether that really answers your question, but what you can observe is that these Q alpha, they are the calculation of when they are fields and when they are real closed fields really has a lot to do with the closure properties of the ordinals. So there is some set theoretic combinatorics going into this, because in the end, it all the only thing that matters is what is the, let's say, additive inverse of a surreal in terms of the length of the length of the sequence, right? So if I give you a sequence of length omega squared plus 1, can you give me a bound on the length of its additive or multiplicative inverse? And so it's the closure properties of ordinals that make sure that the thing is a ring or a field. And this is, I think, in some papers by Philip Ehrlich, who covered these things in
yeah, that might have been some of the literature. I remember his name, and then there was older work by calling him Eiling, who was looking at, I mean, but even long before its real numbers, was looking at classifying real closed fields, basically, or classifying linear orders, which is the main. Anyhow.
So one thing that I want to reiterate here is that the theorems that were on pages 8 and 10, so this theorem here, and also this lemma, if you want that, and then the main theorem, these theorems have nothing to do anymore with the exact construction of R kappa. So R kappa is only needed in order to say that these things exist at all. And in fact, a certain assumption.
The saturation implies that the field is unique up to isomorphism anyway, though, right?
Well, but so you
need, I thought it did.
Yeah. So for the uniqueness theorem, you need more than the saturation, right? You need saturated, Cauchy complete, real closed, and base number and weight kappa.
No, but I mean, I'm saying, isn't it just general model theory that for a given cardinality, there's at most one saturated model up to isomorphism? Of course, this is using a lot of choice, and that isomorphism is not going to be unique or anything.
Choice, we're not worried about choice here.
Okay, because there was also a comment in the chat about choice, and I was wondering if that was somehow another manifestation.
Choice? I don't think I mentioned choice. I may have used the word choice, but not.
Yeah, no, I was wondering. I mean,
choice.
I mean, when you pass to subsequences, you have a definite. You're always able to supply a definite rule. Is what you're saying? It's a bisection argument, or.
Oh, you mean in this proof here? Yeah, of course.
Yeah.
I mean, choice is used. Choice. Oh, maybe I wasn't. I was ambiguous here when I said I don't care about choice. I did not mean choice doesn't matter. I meant quite the opposite.
Right. 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 No, it's just crossing my mind now that, I mean, I don't see why you would need choice to make Conway's construction. And so maybe somehow, there is, anyway.
Yeah.
Long day.
Yeah.
Just waking up.
You're right, still it's still an hour earlier where you are.
An hour earlier than what? An hour earlier than it will be after they change the time. Yeah. I know, that's why I very nearly missed the seminar.
Okay.
Oh, okay.
Any other questions? Oh, I was just going to ask if there are further questions. So go ahead, Aaron.
I just had one question about cardinality, but if a base number is kappa for a field, is it automatically the size of the field is 2 to the kappa, or can there be any more variety?
No, so the Sikorsky field has size kappa. So Sikorsky.
Oh, you can have base number and the
Yeah.
field same size.
In the Sikorsky field, the base number and the size are the same.
Oh, okay. That's interesting. Yeah, thank you.
Anything else? Any other questions, comments?
Let me say something and then ask a question, sort of tangential, because it's about these natural sums and natural products. So first of all, natural sum you described in terms of the Cantor normal form, but you can also describe it without going through that by saying, well, the ordinary sum, alpha plus beta, is the order type of what you get if you take alpha followed by beta.
Mm-hmm.
The natural sum is the largest ordinal you can get by intermeshing a copy of alpha with a copy of beta.
Mm-hmm.
And it's a not entirely trivial fact that there is a largest such ordinal. The question I want to ask is a historical one about calling this the Hessenberg sum. So I'll tell you what I know and then ask if anybody knows something better. In Hausdorff's set theory book, these operations are introduced, and he gives as a reference an earlier book, I think 1906 or so, of Hessenberg. So far, so good. Hessenberg's book contains a definition of the natural sum. I could not find the natural product in there. So my question is, does anybody know where the natural product started?
Since there were some people who said they never heard of the natural product before today, they probably don't know the answer to this question.
Yes, but I was sort of hoping Benedikt or someone else who has might know.
I have to confess that I never looked at Hessenberg's book, so I wouldn't even have noticed that he didn't have the sum. I mean, did he just not define it, or did he say it could be defined and didn't? I mean, did he just not care about the product, or did he forget to define it?
Anything about the product in there? Now, I confess, I did not carefully read the whole book. I just stood there in the library, leafing through it and looking for a definition and not finding it.
And then Hausdorff also doesn't discuss the product, or Hausdorff has both?
Hausdorff has both the sum and the product, and cites Hessenberg for both.
I mean, this must have been within a relatively short period of time, right? Because Hausdorff is 1917.
Yeah,
and Hessenberg is what year?
I think that, I don't really remember, but I think the Hessenberg book was 1906.
Yes, so I would assume that in those years, that there was probably quite a lot of exchange. So it could have easily been that Hessenberg lectured on this and used the product, but it wasn't included in his book. And these years was relatively close, so he might have just known something. But I think for this we need historians.
Can I ask a question? Hello?
Yep.
This is also of historical nature, because I recall there is another paper of Schmerl from 85, which is on some solutions to some old questions of Sikorsky on those fields with Bolzanova-Escher's property. But I thought maybe I will paste this in the chat, what the theorem is about, and I wonder whether this theorem is somehow related to your last, the main theorem of the talk. So I'll just try to paste it in the
I mean, so there is. Let's see what the theorem says.
You know, so there are
Yeah.
models, but
I know. I know this, and I have no idea. We tried to think about this thing with the Aronshine trees for quite some time because there was an open question in the Kiesler-Schmerl paper, which we sort of thought would be connected to these things. And we, in the paper, we even had a whole section on this. And the more we thought about this, the less convinced we were that it really was addressing the original question. So we removed it in the end. So we decided that we don't really have to say anything about this. But it's obviously connected, except that it's not obvious that our theorem really helps anything with it.
All right, thank you.
I just realized that I do have the Hausdorff collected works behind me with all of the commentary that the Bonn team did. So I might even have the tools of finding this out. Purkert may have looked at this when they edited the 1917 book, trying to trace the sources of all of these things. But I'm not going to do this while you watch.
Okie dokie, any more questions? Looks like we're done. Okay. Well, thanks a lot, Benedikt. Nice talk.
Thank you.
And
Quick comment. Next week, we go back to 3 p.m.
Good. Okay.
Yeah, so thank you very much for the invitation, and see you all at some point, probably on screen and not in person, but we'll see.
Until next week. Bye-bye.
Bye, everyone.